Swayam Prabha. Digital India. Educated India.
Welcome back. So we did a whole bunch of reactions on alcohols, redox reactions, acid-base reactions, and so on. Let's look at making alcohols using alkyl halides. All right. So we did that earlier. We took alkyl halides and exchanged it with acid like H2SO4 and made alcohols. Here's another way where you're also increasing the molecular weight of the alcohol by adding alkyl halides to it. An organometallic reagent like Grignard. Grignard is just alkyl magnesium halides. So let's look at some Grignard reactions. Grignard is just the name of the person. And he came up with this very nice reagent, very inexpensive, where you take an alkyl halide, let's say alkyl chloride, bromide, iodide, and you throw in some magnesium into that. And the magnesium has got 2 electrons, right? It's an S2. So it's going to take those electrons and insert into this. It's actually a free radical reaction. And the magnesium inserts 1 electron at a time, and you get alkyl magnesium chloride. So alkyl magnesium chloride. So this is a reagent where you have a metal inserted between an alkyl group and a halogen. I mean, you can think of the oxidation state if this is +2 plus magnesium, obviously it's group 2, and this is group 7. And so the alkyl group is carbon -1. So this is an equivalent of a C-, and the C- is typically in an sp3 form. It's a synthon for an sp3 carbanion. So carbanions are very, very, very basic. pKa is about 50 or above. So extremely basic. So when you do these reactions, you can't have any protic solvents lying around because it's going to instantly protonate and become an alkane. Now, we don't have to go through all of these steps to make alkanes because alkanes can be dug out of the ground, in billions of tons like gasoline. So we want to make sure when you're doing these reactions that it's aprotic environment. Aprotic, because these will instantly protonate if you have any water. This is 50, this is 16 water, or any amine, or an NH2, because that is also about 38, less than that. So anything that has a proton that's acidic, it's going to do this. So this is a note. It has to be aprotic, or you're going to get protonated and literally lose your very nice alkyl group. So this is something we want to avoid. We don't want this to happen. So we have to do anhydrous ether, and that's typically the solvent is anhydrous ether. And I'll just put anhydrous here. It's very, very important that you distill it like multiple times. Now we got this. Well, where's our alcohol going to come in? Well, these are very good nucleophiles as well. They're bases and nucleophiles. Remember the second period out there, basicity increases, nucleophilicity also increases. So therefore, this is one of the best bases and best nucleophiles out there. So here, if you have, let's say, a aldehyde or a ketone, let's say you have an aldehyde, and this is going to be polarized like this, and always your electrophile is your carbon, and that's what's going to attract nucleophiles. Then oxygen's more nucleophilic. So here you're going to add to this some Grignard. It can be some Grignard like this, let's say MgCl, and we just draw it out like that. We actually even put a line between the carbon and the magnesium here. Magnesium's a small element, and so it can handle that. And here you are going to take this hydrogen. This is your minus, this is your plus. So this is going to come in and attack your electrophilic carbon. Push out that oxygen. So we've seen this many, many, many times. This is your nucleophile. That's an anhydrous ether. and that's your solvent, and then this is going to open up, and now you have an anion, and that anion then will go with your magnesium. So your magnesium is going to just go with that Mg, and Mg is 2 plus Cl minus. So you can just, write it all out. So here is your R group. So now you attach that to this carbon here. 1, 2, 3 carbons here. So that's your carbon that attached. In this case, this is primary. It doesn't have to be primary. It can be secondary, tertiary, whatever you want. This is flat. So you have, steric is not really an issue because this is an sp2. And carbon is your electrophile. That's your electrophile. So there is your sp2 electrophile, no steric. So you can add it right there. Now, well, you got to get rid of this, and that's really easy. You do just a workup, a simple workup. Workup means something that you do after your initial reaction to get your product purified. And you can do slightly acidic ammonium chloride, a weak acid, and so you can do that. Basically, ammonium chloride, that H plus is going to produce H3O plus, and so your H3O plus is then going to protonate. So this is pretty much the same as having an H3O plus, very, very weak acid. So here, this is going to then protonate here, and you will get your oxygen in an alcohol form. So here's one way to make alcohols, and your alcohol in this case is a secondary alcohol. So if you start with aldehydes, you will get secondary alcohol. Can you make primary alcohol starting with aldehyde? Yes, you can, but you have to add another hydrogen, not an R group. So with sodium borohydride, you can get primary. If you want primary, you need to start with 2 hydrogens. Because you're putting an R group in, you got to have 2 hydrogens. So if you want to have 2 hydrogens on either side, there's only 1 molecule possible for that. Right? The same formaldehyde, because you need 2 hydrogens, you really don't have that much leeway there. You got to have this molecule and only this molecule alone. So this is formaldehyde. Sometimes it's called formalin. When people die, they put them in formaldehyde because to prevent bacteria and so on from eating them up. So here is, let's say, another Grignard. Let's say bring a Grignard like this, MgCl or MgBr even. It doesn't have to be always a chloride. You can take this and make sure there's no water and hydrous ether, and you can do a attack like this. And you're going to do a lot of these kinds of reactions when you talk about carbonyls. It's all about this, where you have a carbon-oxygen double bond, which is very polarized because pi bonds can get polarized a lot. And so you have a positive that's seeking a negative. Here, your carbon is your negative and your magnesium is your positive. So this is your positive. So here, that's going to go in, and now you can see how that oxygen there is negative, and it's going to go with your magnesium bromide, and you will have this group right here. So your oxygen really literally goes with the magnesium. So now you can just wash out this with the same ammonium chloride. I just draw it out. It's just a mild weak acid, and that's just going to protonate this. And then the hydroxide or water would go with the magnesium, and you would get a nice protonated oxygen there, making it a very nice alcohol. So now your 2 hydrogens on that carbon bearing the hydroxyl, which makes it a primary alcohol. So there's only one way to make primary alcohols using Grignards, and that is by using formaldehyde. And so now your magnesium bromide is going to go away with, well, it's with the water or OH. So you can say this is formal charge minus 2 plus. All right, so that's one way to do primary. So we did secondary alcohol, primary alcohol. Well, what's left? Tertiary, let's see. If you want a tertiary, you have to have 3 R groups here. So no hydrogen. So you have to bring something in that's got R groups here. So there's no hydrogens on that hydroxyl carbon, right? So instead of using an aldehyde, what would you use? That's right, you have to use a ketone. So if you take a ketone, let's say you have a ketone like this. And here too, Grignards are not going to affect double bonds. So you can have pi bonds. But what you should not have is hydroxyls, amines, and so on, because those are going to protonate. So you have to make sure there's no acidic hydrogens out there. So again, you can take this and use any Grignard that you want. Let's use a Grignard that's like this. Phenyl Grignard, MgBr. Those are also pretty. You can take the benzene with the bromine, insert magnesium, and this is a very nice reagent that can be used to insert benzenes wherever you want into carbonyls. So here again, same thing, polarized because oxygen's electronegative. Here is your electrophile, sp2 electrophile. Just like we saw here, this is a very nice carbon, is the electrophile in this case. So carbon, this is your electrophile. Same deal here, electrophilic carbon. So your magnesium eventually finds its way and attacks from the back and opens up your oxygen, which is then going to go with your magnesium bromide. And it's not really going to touch your double bond. So that is a very nice versatile reaction for this. And here is your benzene. Now it's getting bigger and bigger, your 3 R groups here. Now you can take this and then you can hit it with, let's say, some HCl aqueous acid, which is basically hydronium. So that is going to protonate that, and that is going to give you eventually a carbon with a oxygen with a hydroxyl, and it's going to be tertiary. So here's your tertiary, no hydrogens, so tertiary alcohol. So if you want tertiary, start with a ketone. Secondary alcohol from aldehyde, and primary alcohol from formaldehyde. And those are the 3 cases. Well, let's say I have a case where I want to do a Grignard addition, but unfortunately I have a hydroxyl here. So if I put a Grignard in here, it's going to go right for this. It's going to go right for this. I don't want that. What can I do? So what I can do is I can take this hydroxyl and get rid of this hydrogen with a protective group, a group that can go on this oxygen and then come off. So I take off the hydrogen, put on a group that's going to act like an umbrella and protect this oxygen. Then I do the Grignard, then I take off the umbrella and put a hydrogen back. So need to protect OH before doing Grignard, RMGX, then deprotect. So the group that we are going to use for that is called TMS chloride or TBDMS chloride. Either one will work. TMS, trimethylsilyl chloride. Trimethylsilyl means silicon, silicon. And here is your silicon with the 3 methyls, TMS and chloride. TBDMS means third butyl dimethyl. So one of these groups will be a third butyl. Either one's fine. And this one is going to go in, and we will also put in some triethylamine and to deprotonate that hydrogen with ET3N. Okay, triethylamine. Typically, that's the solvent for that. And then you deprotect with That means after you do the Grignard, then you have to take off this group because silicon, they're greasy stuff. Deprotect with TBAF, tetrabutyl ammonium fluoride. So ammonium, that means it's got 4 of these, 1, 2, 3, 4. So it's kind of like a spider, tetrabutyl ammonium and fluoride. The fluoride will bind to the silicon even better than an oxygen. So it will displace the oxygen because the fluorine silicon bonds are some of the strongest out there. These are the most electronegative. It's more electronegative than even oxygen. So it's going to kick off the oxygen by binding to the silicon. So let's do this reaction. Let's see how this will work. So first we got to protect. So same thing again. So you're going to use this first protect with the TBDMS chloride. So SiCl. And so here's again, oxygen's always your nucleophile, and it kicks that out. And it's not going to touch this oxygen because it wants to form a bond here. So therefore it's going to do, this is a carbonyl. If it hits that, it's going to be a positive, which is very unstable. So it's not going to attack that. So here's your oxygen. You have a hydrogen here. You have a lone pair here, positive, and your silicon goes here. And you have a chloride that comes off. Now, well, we wanted to make that neutral, and I don't like people using chlorides to deprotonate because this is a conjugate base of a strong acid. It's completely neutral. So we need to have a nitrogen ET3N, ET3. So here's your spider crawling up the ladder and coming over to pull off that. Your spinsy spider there is going to do the job for you. So you got now your silicon holding on to the oxygen, and it's nice and neutral. This is OTMS. So you can, sometimes people write this as trimethylsilyl is OTMS. Now, this is then going to add a nice Grignard. So you can bring any Grignard you want, any R group out there. Let's say I bring in even a very sterically hindered third butyl group. You can do an SN2 with this, but for Grignards it's okay because a lot of the Grignards are single electron reactions. So now that's going to come out. Now you've done this, then you don't care what happens. This is the one where you need to be anhydrous. So all this time there's no acidic hydrogens here. So now you have your silicon hanging off of that, protecting that oxygen, alcohol group. And here's your oxygen popped open, O minus, and that goes with your MgCl. And you will have your R group here. So the R group is going to come right here. Now you can take off the silicon and just wash it out with some water, and you will get your nice tertiary alcohol. Here we started off with a ketone. You can also do this with an aldehyde. I just happen to have a ketone. Now, as I said, use the TBAF. So your TBAF is going to come in. So put TBAF, and we have the structure over there. Your fluoride is going to kick in, and you have your ammonium, and then that's got some water and so on, and that will protonate that, and you will get this OH, and then here's your oxygen, OMgCl, and that would also really come off, and you would get your tertiary alcohol. In an aqueous environment, you will have, let's say, water. You can protonate that, and then you can get your tertiary alcohol. So this is one way we always do protection, deprotection, in order to make sure that your acidic hydrogens are not eating up your reagent. In this case, if you have an OH or even an NH2, you can protect your groups in order to do your Grignard in a very anhydrous environment with no acidic hydrogens. and MgOH, magnesium chloride, is going to fall off with OH or fluoride probably. And so we have a ketone going to a tertiary alcohol. So that's one way to do protection, deprotection for Grignard, mainly to get rid of acidic hydroxyls. So don't hesitate to ask me if you have any questions. This is simply a way of adding an alkyl group to a carbonyl to create a larger, more substituted alcohol. So just to summarize, an aldehyde, when you put an R group in here, is going to give you an alcohol with one hydrogen, that is secondary. If you have a ketone like this, you have two R groups, no hydrogens. When you put another R group, you'll have three R groups on that alcohol, 1, 2, 3. That will be a tertiary. The only way to make a primary is with this single molecule. You have a carbonyl with two flanking hydrogens. Those hydrogens will remain. You can't really break off CHs unless you're doing some oxidation or some very vigorous reactions. These CHs cannot be pulled off because the pKa for CHs are really, really very high. So pKa of a CH is about 50 to 60. So you can't really pull them off. So you are not going to pull off these hydrogens. It's the OHs and NHs that can be pulled off. So here your R group is going to attack that. And now you're going to have two hydrogens on your carbon bearing the OH. That's a primary. So in cases where you have alcohols already pre-existing on the carbonyl framework or on the molecule or amines, you really have to make sure that these hydrogens are removed before the reaction. Otherwise, they're going to protonate your Grignard and make them into alkanes, which you can really dig out. So therefore, you take that hydrogen off and you put a silicon group that can be removed after you add your Grignard reagent. All right, so if you have any questions, guys, don't hesitate to ask me. See you next time. Bye.